All right, welcome. Thanks for the kind introduction. So this is a talk about anomaly detection and fault isolation in PIM IGMP multicast video packet streams. And of course, when you do machine learning and data science, you need a labeled data set. And of course, we didn't have one, so we used ESP to make one. And so I can sense some skepticism. But before we get going, just by show of hands, so we are, a couple of hundred people. May I ask how many of you, just by show of hands, come from kind of the electrical engineering, computer science? Okay. All right, good. Physics, physical chemistry, that'd be my cohort. Good number of you, okay. Of course, the other engineering disciplines, okay, good. Oodles. Among those, how about industrial engineering? I know that's a really good, yeah, with all the supply chain stuff going on. Yeah, good. How about, for example, bioinformatics, computational biology, molecular biology? Several, okay. Social sciences with heavy statistics, design of experiment, human factors. Several, okay, good. All right, well, we're all in the right place, so good. Well, let's get to it. So here's the basic business case. So the idea is you've got some kind of fault in a network operations center. A piece of gear goes down or something, or just the stream gets corrupted by shot noise or who knows what. And those are usually, it takes time to detect it and isolate it. Where is it in the rack, X, Y, and Z, and so forth. Those are measured with average times. You very rarely hear about variance in those things. It rarely comes up. Then you've got to restore it, which usually involves some kind of failover pathway in the network. And then when you have, and about that time, the customer call center just lights up, and periodically customers will tell you something you don't already know. I mean, especially if it's outside the NOC and out in the field, of course. But if it's in the NOC, your call center is arcing up to field calls about something which you already know. And so, and then when you have the luxury of time or not, then you have to repair that gear and get it back in the rack. And so, it's compelling to think, if we could predict this stuff and get out in front of it, if we knew when and where. So, it's like Einstein, right? Time and space. So if we know when and where, and then we can kind of proactively fix it, and there's a term for that. It's called proactive grooming. The network engineer folks will proactively groom, a Cisco router or an Eris ad insertion server or something like that. And then, of course, you can fix it in a planned way. And any time you can convert unplanned maintenance to planned maintenance, that's a winner. Whether it's rolling stock, which means trains, or whether it's aircraft engines or whatever it might be. Any time a unplanned maintenance activity can be scheduled and planned, that's of course better. And a lot of your ROI here, maybe all of it, is actually in the customer call center, because it's very expensive to field those calls. And if you can intercept those and tell from the ANI exchange number maybe where it's coming from, and offer them a message that you're on it, and reduce the labor cost and especially the overtime cost in a call center, that may represent a good amount of the ROI. So it's not hard to find this stuff. If you do some RCA there, among high-speed internet, VoIP, and multicast video or video at all, of course, it's all in video processing and transport. That's really where the major cost comes to offer good customer service and to mitigate the effects of disappointed customers. So here's what we did. This is kind of a toy representation here of a network operations center. You see some, not shown is a satellite dish in the head end, but then there's some backbone routers and core routers, some distribution routers, some access routers. That NXS is either virtualization or firewall or both. And there's a system clock, and so you put some taps there, which is a hardware piece of gear to intercept some packets, and then a pretty sophisticated API to strip the headers and look at the payload and see what's going on in those packets. And so starting up here, you've got some 1 second sliding time windows, which is huge because this stuff is streaming at 50 megabits a second, that kind of a number. So you have some entropy information in that's 2% of a microsecond, right? So so 1 second is just an absolute eternity. So we chop these things up with 1 second sliding time windows. That's kind of an arbitrary and capricious number, but it makes sense. We strip them, we stack them together in kind of this motion picture type thing and do some calculation on it, and then we, as Theo mentioned earlier in the day, we can do some histogram analysis or some, in that case, classification. I don't know if that looks like a Pop Warner Little League football playbook, but it's supposed to be a sport vector machine, I think. And then you can measure some quality, so true positives and false positives and all those confusion matrix things, precision recall, all that stuff. So that's the gear, and that's how we wire it up. But when you do these classification schemes, of course you have to have a labeled data set. And we don't have a labeled data set, man. I mean, this stuff is streaming by. You record terabytes every time you do a hypothesis test, and if you had a couple graduate students, you could just cut them loose on labeling the data set. But I don't have any graduate students, so so we had to figure out a way to do it. And so we started to think, is there any place in engineering and science where you kind of the system tells you about itself, and I mean, this is old stuff. I mean, that's Walter Shewart there. Bell Labs, Western Electric, Champaign-Urbana in Berkeley. Trained as a physicist, and he was kind of the father of statistical process control. And so his idea was that when you have a gremlin in the system, that it manifests itself effectively as a drift in some quality metric. So you look for a blemish on a widget and try to determine is there a gremlin in the system who's kind of changed the physics of the thing, and you look at the drift in quality, and when you have a certain loss of quality measured by a standard deviation. In his writings, he often looks at 3 sigma, but nowadays I think maybe because of the increase in quality of measurement, it's common to use 1.5 sigma events. But anyway, that's kind of applying some statistical inference to some kind of drift on a quality measure, and that. He did his work in 1931. If you think about that, I'm not much of a historian or anything, but Bell Labs, laid off 80% of its workforce in the Great Depression. And between 1930 and 1933, they laid off 80% of their workforce. And at that time, the most important technology in their system, arguably, was the vacuum tube. And that was something that was stewarded through a very difficult process by master and journeyman glass blowers. So, if you lay those guys off and you revert to apprentice glass blowers, I mean, they're very capable, but you can imagine that they had to do something to stick some quality measures on there. That's just conjecture, but so that's the idea, and that set off a series of scholarship. There was a depression there and a world war, but you can see once prosperity returned. E.S. Page there he was at Cambridge and then Durham in the UK, started to think about continuous inspection schemes. So the idea was, can you kind of look at these blemishes on the widgets as they roll off the conveyor and say something about them as a continuous sum? And then Roberts, also at Bell Labs, and Shuriev, who was at Moscow State, and Manchester, I believe, in the UK, both kind of picked up the ball and tried to say something about optimizing that. Roberts really did a lot of work in geometric moving averages, whereas Page was kind of thinking about continuous sums, and Shuriev thought about exponentially weighted averages, and so they made some gains. And then there was another scholar there, George Moustakidis, who actually was very near here as we stand here in city center of Philadelphia. He was over at Penn for a master's, and then had the good humor to go be a Princeton Tiger, where he took a MSc and PhD, I believe, in electrical engineering. But he's really, as recently as '86, was writing about these things and kind of showed that for certain classes, especially of stochastic processes, Page was right all the time, and despite the benefits of geometric and exponentially weighted moving averages, that Page's continuous sum is optimal. Page's E.S. Page, I call him ESP for short, so I might have misled you there on the extrasensory perception stuff, but you'll see why E.S. Page is just as good as ESP for this class of problems. So here's what Page was doing. He said, you've got a time series here, or at least a series in time. Not necessarily a time series, that's a term of art. But, whereas Shewhart was trying to say something about the statistical inference of drifts in quality metrics, the physics of what's going on is the gremlin gets in there and pushes the bell curve to the right. So you see down there 7 2/10, that's 1/30. So treat that kind of as a monthly defect. Maybe a bolt comes loose, or some lubrication on a conveyor becomes deficient on a 30-day time scale, or maybe there's a new apprentice who really is not a capable apprentice, and that person on the conveyor that day causes a defect in a product, or something's happening on a 30-day periodicity. And what the gremlin does is shifts that to, let's see, 7 and 23 would be 30, 32 tenths is 1/7. So he shifts that to a weekly defect. And the question is, how can you know, and when will you know? And with what quality of true positives and true negatives can you know? And those of you who have played around with normal random variates or any other random variate from a cumulative distribution function or a probability density function can probably guess that just because there's a weekly defect, you won't know in a week. It's going to take you a while. So that's the game that's afoot here. And so I don't want to get too lost in the arithmetic here, but it is a data science and artificial intelligence conference. So let's just kind of reaffirm kind of this formulation that all of us have seen probably in the context of a logistic regression formulation. I'm sure everyone's been through that kind of formulation. So the idea is you have this telemetry of IID events, and so it's the product. And let me just walk you through the notation because it's kind of tricky there, and then we'll move on. But you see the change point in the denominator there is time I. So at I, the gremlin shows up at time I and pushes the bell curve from a 30-day process to a 7-day process. And so those red K's take you back in time. So from prior history back in time up to the change point I, then you've got these IID events with a probability distribution over X parameterized by theta, which in this case is mu and sigma. And then the numerator, the yellow guys take you forward in time. So from just the other side of the change point there, J is I plus 1. So just the other side of the change point, far into the future then, I plus K, where K is now taking us forward in time. You've got this other PDF over X, parameterized by theta prime, which in this case is mu plus delta. Now, those are Gaussians, and we'll leave sigma the same, just so we can get a closed form solution here. Of course, in simulation, you can let sigma vary if you want, but not right now. So they're products of Gaussians, and of course, a product of an exponential is a sum in the exponents, right? So you've seen that. So we've got this odds function here, and I've done the arithmetic for you there. So let's think through that. So before the gremlin shows up, and we're picking normal random variates from the orange, okay? Then the denominator is going to be bigger than the numerator, and so the odds are less than 1. So as we went back in time before the gremlin showed up there, the red K minus, K less than, that thing's going to be less than 1. Then once the gremlin shows up, then the numerator is going to prevail, with some exceptions. There's a red-orange area there, right? So the gremlin could hang around on the left side of those normal random variates, and you wouldn't really, you'd be none the wiser, right? But even though the gremlin's there. But anyway, so that numerator is going to prevail eventually, and so that fraction would tend toward 1. If you take the odds of the log of those odds, so now it's a logistic type thing, then that's a condition over 0. Okay, so to me, a guy of my mediocre math talent, that's just kind of a cool algebra result. But to a genius like Page, that is an absolute innovation in statistical quality control. Because what he said is, now let's think about that. What he said is, as long as sigma is constant here, then as that thing slides from mu to mu plus delta, halfway is mu plus delta over 2. And if I take a normal random variate, remember I don't know when the gremlin shows up. I have no clue. So if I just take whatever normal random variate is presented to me, either under the influence of the gremlin or not, and I subtract off delta over 2, then on average, before the gremlin shows up, you can see the delta over 2 line there. In general, with some exceptions in the red-orange area there, but in general, I'm going to be drifting downward. Because when I take mu plus delta over 2 and take that away from a normal random variate in the red, that's going to generally be a negative number, again with some exceptions. But once the gremlin shows up then, again with some exceptions, those yellow normal random variants under mu plus delta and sigma are going to generally be positive. And so if you look at drift in a continuous sum way, I've got another picture of it here. If you look at drift in a continuous sum way, it's going to drift down, and when you find a minimum, then that was the change point. Now be careful, because just because there was a change point doesn't mean there's a minimum. And frankly, I've got a simulation. I don't want to get off script and show it to you, but anyway, I made a simulation, and you would be surprised how many times you've got to rerun this thing to get a picture that looks like that. So this is a 1957 paper, which means throughout 1956 there was some poor graduate student who was picking normal random variates and rolling dice and trying to get that chart. But yeah, I know. But anyway, that's yeah, I know. Just glad it wasn't me. So that's the trick. Now it's not all roses, because this is a simulation I built in Excel VBA here. Let me walk you through this. So the idea is you have arbitrary units on the left. The blue line's in weeks, and the average run length is your average time to a false positive. Your average time to a false positive. The red line is the mean days to detect. So the gremlin has showed up. Okay, so the gremlin has shown up. And he's wreaking havoc once a week. So how long will it take? Well, down there at the bottom, you can see I think that number is about 15 or 18, that kind of thing. So it takes a couple, 3 weeks to kind of catch on to the gremlin who's causing a weekly defect on average. And when you do that, you'll have a false positive if you put the math traps in place. Okay, you'll have a false positive. It looks like every 70, 80 days. So in other words, if the gremlin didn't show up, if the gremlin does not show up, but you've got the math traps in place to catch a weekly gremlin, then using a page continuous sum process, you're actually going to have a false positive, every 3 months, that kind of thing. Yeah, no, that's right. Yeah. And so it's compelling to think, well, I'll just raise the threshold. I mean, I'll raise the threshold to where I'll immunize myself from false positives. And so if you're willing to live for 180 days before you act on your weekly signal, then what is that, 700 some weeks? I can kind of immunize myself from false positives, and that's compelling, because remember when they were doing this work, to chase down a gremlin, you had to lay off a couple, 3 shifts of workers or more, and you had to tear down some big physical plant maybe and fix it. So I mean, you hesitate to act on a positive of any kind, false or true. But it turns out that it is horribly heteroscedastic. It's just absolutely horrible, and that's 1 sigma. So you can see that even if you take a very high threshold, and you can see that when you take a very high threshold, you don't give up a lot of days to detect. You go from kind of 15 days to kind of, like 35, 40 days. So if I'm willing to wait 35 or 40 days, it seems as though I won't have any false positives at all on any kind of reasonable time scale. But indeed you will, because the heteroscedasticity just catches up to you. That's just a 1 sigma at 95% confidence. You're going to give it all back. You're going to be back down on the baseline. So the message here is don't try to beat the false positives. You're not going to do it. Just pick your threshold to manage your business, and so that you get the right mean time to detect in days that makes sense for your business. If you can live through tearing down a machine every 40 days, then that's your answer. Yeah, exactly. So. Okay, so anyway, Page, continuous sums, Surieff's exponentially weighted averages, and Roberts' geometrically weighted averages, they tell us how tally the signals, but like what signals? I mean, we don't have blemishes on widgets coming off the conveyor belt. We've got 50 megabit a second PIM IGMP packets streaming through a multicast video network. What signals? And so we had to figure that out. And there's a good body of work on this on another topic. It usually has to do with hacking and trying to break encryption and that kind of stuff. But we piggybacked on that. The idea is when you compute on packet streams, you can imagine you want some kind of metric that is sublinear, certainly, and polylogarithmic if possible. That is logarithmic not only in the number of the given each species, but also the total number of packets. You can't store it in memory, it's streaming by, so you've got to run some kind of metric on it, whether it's Gaussian statistics or something else. And we've done quite a bit of work, many on our team, and especially in optical regions for laser studies, but many of us come from physics and physical engineering, and a few from computer science and information theory, but we kind of thought about entropy as a metric, and we like that. And these are just two papers. There are dozens, but we kind of picked up on these. This MIT group, because they kind of defined a sketch, which is kind of a frame across different reference frames of the network and the entity diagram. So we liked what they had to say. And then this team, I don't know this blended team, but Ashwin Lal I know was a postdoc at Georgia Tech, I believe. I've read a few of his papers. So anyway, there's a blended team here. Somehow the Rochester kids and the Georgia Tech and the CM kids know each other, but or colleagues somehow. But so we decided that entropy was it, and so we started to do some thinking about entropy. And this was a light lift for me, particularly. I was trained as a chemical physicist, and a bit of my thesis work involved this kind of thing. So I was on at least familiar ground, but had to catch up my reading a little bit on this literature search. But there's a little simulation I did. That's just what I'm doing is rolling one die, a six-sided die, and there's more jitter in that left-hand baseline than it looks like. But at this scale, you can't see it. But anyway, it's fairly uniformly distributed as you might as well as you can expect from a Excel pseudo-random number generator anyway. But then at an arbitrary time, I flip a button in the simulation and throw a seven-sided die, and you can see that the entropy renormalizes there. And what's really cool is if you just put that seven-sided die in the simulation, I think I was pulling 10,000 uniform random variates here. Just for one hypothesis test among the simulation, then you see it kind of stands up off the baseline there. So it's very robust. I mean, these gremlins are very egotistical little guys. They'll stand up and wave at you if you can get the right probe them with the right math traps. It is important, though, that you define entropy properly, and what the MIT kids helped us with, I believe it was, it might have been Ashwin Lal's paper, but you don't need the full Shannon entropy. First of all, it involves a division. You got to get to p log p, and it's really not necessary. You can probably convince yourself if you work through the algebra there of H that you can get to this entropy norm term in the sum that just leaves the number of each species as a raw number log times the log of the number of each species. And what you're after with these logarithms, remember, that just lets you take a product and convert it to a sum. So as long as you can live with calculating a logarithm and multiplying it, then you can get away with that. And it turns out real nice. I just in Excel VBA wanted to get the timing. In my C++ days and my C days back on Wall Street, I really worried a lot about the cost of doing arithmetic on streams, which you're doing when you do Gaussian statistics, right? Because the average has a division in it, and everything else is worse than that because they're functions of those earlier moments as you go through variance and skewness and kurtosis. So. But anyway, just in Excel VBA, if you ask for 1 billion floating point calculations on Shannon entropy, it takes 2.5 minutes, and it's 1:45 there with just this entropy norm as defined by the in one of those papers that I showed you, and so that's a 33% difference, and it's not the end of the world, but you're going to see we had some back pressure anyway on the Kafka and Zookeeper circuit, so we on the Apache stack. So 30% is a lot, and so if you don't have to spend it, don't. That's the message there. I know many of you in this room have more to say about that. But anyway, that's just a way to show that division is very expensive. So don't do it if you don't have to. And if you're looking for quality metrics here on these packets as they stream by, and maybe Gaussian statistics aren't too good because they're full of divisions. A lot of arithmetic in Gaussian statistics. So here's a little simulation I did. That thing on the top here is just a simulation for my bosses to show them our vision. There's an egotistical gremlin kind of waving at us every once in a while, but that's just my artwork. But this thing on the right, these packets per second on a given VLAN, and I've coded it 1, 2, 3, 4 because I don't know if that would give away our client or not, but we're not going to go there. But that's CNN. CNN on a given VLAN in October there as we were doing a hypothesis test. So we're trying to catch the entropy there of those packets, and you can see that we were actually doing it. And then we also did a ratio of 2 taps. Remember, those packets appear at different times, separated only by nanoseconds. But if you know what you saw upstream, then you bloody well better see it downstream, right? And so that ratio should be absolutely flat, and of course it's not when there's an anomaly. Let me talk you through this little Excel spreadsheet simulation. This is what we did to get ready to put these math traps in place to catch these anomalies and isolate faults. So this is a little simulation we did. We built it on a 30-second commercial that we took out of a football game. So we recorded it through Wireshark and kind of washed it out and built this. So what you're seeing is just a packet simulation. You've got a time bin there. And the duration was in hundreds of, I guess it doesn't matter, but hundreds of microseconds. Could that be right? Or 1/100th of that. Anyway, but so you've only got a few packets per time step, and so we're just kind of watching the Gaussian statistics as those anomalies, or sometimes just natural binning, work their way through the wave packet. So just imagine this wave packet streaming by. I don't mean the PIM-IGMP internet packets. I mean the probability density wave packet as it floats by. So you got in there as a count. You got the average on that count, the variance of that count, and then in the higher moments we calculate the first 4 moments and take functions on them. So skewness, which is a function of your first, second, third moment, and kurtosis, a function of the first 4 moments, and then this entropy norm. And what's interesting, one of my colleagues, who's a particle physicist, was at Fermilab for years. He said, we looked at this. Isn't the envelope of the variance kind of the same thing as the envelope of the Shannon entropy? And of course, he's right. You can see there that the envelope of the variance is very much like this entropy norm. But can you see? Is my mouth? Yeah. Can you see this particular peak here, where the entropy is rising and the variance is shrinking? And it's not the end of the world. There's going to be plenty of signal for Page's continuous sum, or Roberts's geometric sum, weighted sum, or Shuryev's exponentially weighted sum, or exponentially weighted product. But you do get a haircut when you calculate those sums, remember, when they contract. And maybe to explain this, imagine I had 5 numbers, 0, 0, 100, 0, and 0. The average is one fifth of 100, so it's 20 with a pretty big variance, basically the size of the with the standard deviation, basically the size of the average. And that entropy would have a certain value based on 2 species. They would have 4/5 log 4/5 and 1/5 log 1/5. Now imagine that crazy 100 peak shrinks to, say, 2 peaks of 1 and 2 in height. So now I've got 0, 0, 1, 2, 0, 0, which has a much smaller variance, But it's 3 species now. So actually the entropy norm would increase. And remember, the physics we're tracking have to do with defects. we don't care the size of the defect. The electrical engineers that make these IEEE RFC standards, when they say 1,362 packets, that's what they mean. They don't mean plus or minus 1 or 2. So we're not really that interested in the size of the defect. The fact that there's one at all is what we're after. And so my colleague's right. I mean, the envelope of the variance is very much like the envelope of the entropy norm, but that doesn't matter. We went with the entropy norm because it really models the physics for us better, which I think is really what the MIT kids and the U of Rochester kids were saying all the time. Well, that's what we planned on. This is what we found. So let me walk you through this. So we've got 3 rows. We've got packets per second flowing through Kafka. Remember, we've got some hardware there with a really sexy network interface card and that's Hitachi intellectual property and an API that lets us basically take packet level sliding time window statistics on the packet stream and tender it up to via JSON token, and it transits Kafka to our dashboard basically. And so what you're seeing is the trace, a moving average on that trace is the red line. We've got packets per second, megabits per second, and then the ratio of that megabits per packet. And the Gaussian statistics, the entropy norm is off camera here. And then there's a Wireshark trace spanning, I don't know what that is, 1806 to 1901. It's about a minute. Looks like it's about a minute there. So and so that is decidedly not a flat line with a few gremlins waving high, whatever that is. And the electrical engineers tell us that's kind of back pressure. And I don't know what I'm talking about. I know some of you would, but it has to do with when Linux manages Kafka and Zookeeper and Cassandra and all that, the buffers kind of get backed up, and it comprises a kind of a back pressure, like a plumbing circuit, has a back pressure. And so we're seeing this back pressure, and so but in there is the signal. I mean, the gremlins are in there. It's just now they get to hide among a lot of noise, and so the question is, what are we going to do? And so this is just 5. I've got thousands upon thousands of these things. But this is one particular hypothesis test that we were working on in October of last year. And so this is just 5 of thousands. But the second one there is epoch 39, and you can see that it kind of goes from a nice trace, fairly calm with a fairly flat moving average, and the trace goes to 0. It goes to ground, and then kind of resonates for a little bit. Remember, those are 100 those are 100 sliding time window epochs. So at epoch 39 there, the thing went to ground. It sort of rang around for another minute and a half, and then kind of the platform health kind of increased there a little bit. And so we took an interest in that. But what are you going to do with that? I mean, it's not a time series. I mean, it's a series in time. I mean, it is a series in time, but it's not a time series. This was not hard to prove, but by negation, we just showed it. First of all, it's not static. I mean, I think you can see with your own eyes it's not static, but is it stationary? I mean, does it have a constant mu invariance, and is the covariance just a function of the time step? Well, no, not even close. We tested this across probably, I don't know, programmatically 100 or 200 sliding time windows. Just 1 or 2 showed us that it failed. But and remember, you need these conditions because if it's a single data generating process, like business data coming out of a business firm or economic data coming out of a national economy, it's under the influence of monthly events and weekly events and quarterly events and secular and religious holidays and shopping holidays and tax holidays and things that you can model in a causal factor matrix to calculate betas. Whether you do it with normal equations or descend the gradient, however you get there, the betas are constants. They're not time variant numbers. They're not functions of time. The betas are the betas, and of course you've got a mean absolute percentage error or some kind of positive definite measure of quality, but the betas don't move around in time. And so anyway, this took almost no time to prove to ourselves, but the onus was on us to try to show that. So I just thought I'd mention it here in the context of a gathering of data scientists. But once you're at this point, we were kind of stuck. Of course, we know how to get unstuck, but I mean, at this point, we had to take a breath because you've kind of we didn't know what we didn't know, and you've kind of seen this kind of tired cliche about the arrows. The arrows are when the centroid's over the bullseye, that it has good accuracy, and when the arrows are tightly grouped, that's good precision, and you'd like to have both, of course. But that's school. In school, they give you the problem, and you have to calculate the answer, and that doesn't bear the slightest resemblance to what we do for a living, does it? I mean, when Mother Nature talks to us, she doesn't tell us the scale or give us the bullseye. I mean, we've got these red arrow points sticking through the back of the target, and we look at them, and we don't know what that is. First of all, those are, whatever they are, they're probably projections of some point cloud in hyperspace, causal factor space, that are projected onto some basis, but I might not even be looking at the right basis. I might not even have the right basis set. So you have to start doing some tests. But anyway, the problem is that could be neither accurate nor precise. It might be accurate. That looks pretty accurate. It's not precise, or maybe I've just got the scale wrong. Maybe they're accurate and precise, or maybe this is just not well defined on this projection. Maybe I've got the completely wrong basis set. So anyway, there's kind of a way out of this that was given to me by my doctoral advisor years ago, and it's just a nice little trick. If I could remind you of Kolmogorov-Smirnov here, the KS supremum formulation. The idea is you take a cumulative distribution function, a baseline cumulative distribution function, in this case N01, and you write it down. And then whatever problem domain you're working on, you sort that and scale it as a cumulative distribution function, and you write it down. And the maximum difference between those two is a test statistic. It's called the supremum, and indeed, I think it was Smirnov. I haven't read this paper in 30 years, but I think it was Smirnov who actually published critical values for especially the N01 cumulative distribution function, the reference function. And so you can do a test of statistical significance the way you do a z-test or a t-test or a chi-squared test or an f-test and so forth. And so he published these things, and just to kind of show you, this is a simulation I built. This is just a little Excel VBA here, but I took 10,000 normal random variants. I took 25 epochs of those 10,000, and then just by random I inserted not other N01 normal random variants, but I inserted some uniform random variants across those 10,000, and then calculated the supremum and plotted it. And I think you can see where the two epochs of uniform random variants were. They're right there at times 6 and 13. Those two lines are just for scale. That's a moving average, a 10-period moving average with no offset, and then 1.5 times that. That's not even a real thing. I just used it so we could get some scale. No false positives on that scale, and you can very clearly see where the uniform random deviants were kind of injected as a gremlin into the KS simulation here. We're not doing statistical inference really. Remember, I'm at liberty to actually not work that hard. I can just draw a threshold and then calculate a confusion matrix. So actually, I have it much easier than Smirnov did. But so here was our approach. So we took and we did this in FFT time, of course. But anyway, here's a little slide that our motivation was Fourier, and so we took these crazy epochs here. Each one's different, and we had our electrical engineers look at these things and some network platform health experts, and we said, you tell us when there's 100 seconds that's very well behaved. No funny business, no remedy tickets, just you look at it and use your, I think it was probably 300 or 400 years of combined experience, and you tell us when that thing looked good. So we transformed that thing. Of course, you only need the upper half plane, so you don't need this Rorschach test looking thing there. Sorry about that, but I had all, whatever that was, 64 or 128 dots, and I just put it on a chart. But that's really not probably the way to do it. But, so that red line, that red Rorschach thing is our reference to what the experts told us was a very healthy platform. So those red dots there are like the KS N01 red line there. And from that, we then plot everything, including their Epoch 39, and look at the blue dots on these crazy busy Rorschach things there. And if you norm those in theta and R, so each one is in phase space there. If you norm those and write them down, what you'll find is almost all of them, thousands upon thousands of them, all kind of lie on top of each other. Except when there's a gremlin, and he just can't help himself. The little egotistical guy kind of stands up and waves at you, and there he is, Epoch 39. And this gave us an idea. And by the way, those are in raw numbers. I don't even know. Those are in arbitrary units. Remember, if I normed those out from 0 to 1 and pretended it was some kind of cumulative distribution function, maybe that would be more genuine to Kolmogorov and Smirnov. But I didn't do that. I left them in a raw way because I knew I had an idea. E.S. Page in 1954 sort of talked about this, that when you have a telemetry or a trajectory in a space, and you draw a resultant vector to it this way, then the angle between the vectors becomes a test statistic, and it is indeed distributed. E.S. Page in 1954 actually published critical values for binomially distributed random variables, random variates. And so we actually calculated that distribution, and we were able to set a threshold. And but that wasn't really that impressive because Short and 31 would have caught this thing. I mean, look at that. That is the blue line there at the bottom is just a moving average. I don't remember what or I guess just a raw average. But look, there's 1 sigma, 2 sigma, 3 sigma, 4, 5. That's a 5 sigma event. I mean, you can see that thing from across the room, right? So that's kind of cool. But look at Page in 1957, where we have this cumulative sum idea. And I've actually swindled you a little bit. I've pivoted to a Shuriev exponentially weighted moving average, and I did that for a very, very nerdy reason. I did it because Kolmogorov was Shuriev's PhD advisor, and it's just my nerd way to kind of tip my hat to that academic family. I thought that was kind of cool. Once I was deep into this problem, and Kolmogorov and Smirnov could kind of get me unstuck, then I thought maybe the least I could do is throw kind of Shuriev in there and calculate it that way. But whether it's a cumulative sum or an exponentially weighted thing going on, you can see that it stands up off the baseline. That signal actually was getting kind of busy at epoch 28. So that's 11 full epochs in front of the actual event. 11 full ones. And that's a big deal. That helps us remember, I'm after a labeled data set for anomaly detection and fall isolation in a PIM IGMP packet stream. So, what label? I mean, I can't just sit down and label a data set, and I'm sure we've all done that in here, but now the system can label it for me, you see? So that's a big deal, and I can do it, terabytes at a time. I turn it on and I go home and go to sleep and come back. So what this lets us do is, ESP in 54 would have said, there it was, I saw it. And Short definitely would have caught it, there it was. But ESP in 57 has a way to say, hey man, here it comes. Get ready because here it comes. And so that's helping us get to our goal of getting out in front of this thing and converting it. Really at the end of the day, our challenge is to convert unplanned maintenance into planned maintenance for enhanced customer service. So here's our labeled data set, all the telemetry from the taps. It's time and space. We've got an entity space diagram, and we can figure out where that packet is on the network by doing a matrix multiplication and just like you would in an entity diagram space. We've got all the Gaussian moments, but I don't recommend them. There's an awful lot of arithmetic going on to get Gaussian statistics. But if you have the luxury of time and can calculate them off time you may as well do it, but the onus is on you to calculate those at runtime for the stream, and I submit that would be a challenge. The entropy norm, of course, is our workhorse. The KS soup we used over a whole host of baseline distributions, and all of Page's phi statistics on those crazy FFT vector norm things that we created. And then all of the change points, all of the ESP change points for various multipliers and thresholds. So we've got a whole causal factor matrix of all kinds of games with multipliers and thresholds to try to see what lifts off the baseline is most statistically significant with the highest quality of precision and recall and sensitivity and specificity and all that stuff. You can do cluster analysis on these things. Once you've modeled them up and all of the binomial labels for all kinds of combinatorics over causal factors, we can label them, and then we got some principal component analysis, which is another benefit of the FFT because we can take really the largest coefficients of that FFT, and we don't really have to diagonalize matrices. And these matrices are huge, so all of a sudden we don't have to. On each epoch, we just simply pluck the coefficients we want. It's not hard to find them. It's easy, and then of course we center and scale everything, of course. So there it is. We saw all these things on segments and channels. We can do it for high def and standard def both. And the big win here was that in October, in anticipation of the final presidential debate, we were running these hypothesis tests in a certain head-in in a certain geography in the country. And remember, the ROI here is the call center. And so we actually did just some good old-fashioned statistical analysis on the call center logs. And in the footprint of that head-end, the user experience is measured by call center activity and social media was significantly better. Social media did not light up in a derogatory way. The call center did not light up for customers wanting to know what was going on with their service vis-a-vis the rest of the country. We were 11 full epochs, that's 1,100 seconds, 1,100 sliding time windows. You can see that gremlin lift off the baseline, but we've got it down to 1,000,002 now. That's 2 full weeks, and I just want to take a minute to explain that. I know many of you have worked. I had a conversation at the coffee pot here earlier in the day. A few of us were on Wall Street together, and this model has served us all well. And I said, well, I'm actually going to bring that up. What this is an earthquake model. You've got some blocks of various sizes. You've got some bungees and springs of various Ks, spring constants. They're all sitting on a corrugated crystal surface there. You can see that the blocks are of varying distances from that corrugated crystal surface, corrugated surface, and that's not an accident. Some of those slide right along the surface, and some of them have a higher mu coefficient of friction, and so forth. And the game is that this top bar here just kind of unceasingly just moves to the right, an inch, centimeter per year, or whatever. What you would find, if you look at these two distributions at the bottom, let's focus on the left one first, is what you would find is as you pull that bar with all these randomized block weights and couplings, is that eventually one of those blocks would give way and release a little power, because there's work on it and there's a displacement. So it's a power over a 1 second or a microsecond time scale, whatever you're measuring. So it's a work per unit time. And you'd have a bunch of little ones, and then if you think through it, eventually that thing would be an elastic equilibrium. It would just sort of sit there while that bar continues to move to the right. And so if you look at the time series on the right, you've got a little one and a little bigger, and there's a bigger one and a little one, and then it just kind of rests while elastic energy builds up as that unceasingly advancing bar on the top moves forward. After which all hell breaks loose, because when the big one goes, it's going to release an awful lot of displacement and an awful lot of energy all at once. And the moral of this story, which any earthquake scientist knows, or geophysicist, or as it turns out, a good number of algorithmic quants on Wall Street in sell-side finance, what you realize is that the little ones don't relieve pressure on the system. The little ones set the system up for catastrophic failure. You don't have to take pictures. This is on my GitHub. So yeah. Oh, you take a picture. Yeah. But build this model for yourself. It's a heavy lift. You'll have to work at it, especially for an arbitrary number of blocks and bungees with randomization. I always use kind of a random energy model for those bungees, so that works well. But that's the message there. And so when I say we can see it 2 weeks ahead, is when we went back and looked at data that gave us that signal at 11 epochs. That gremlin had been in there a couple of weeks bouncing around. We just had to get the right math traps in place to see them. And this is kind of how we did it. So that's kind of abstract, but I'll leave it there for now. So this is kind of cool. I mean, it's new stuff. The data science is new. The electrical engineering of this problem is brand new. I mean, it's brand new Hitachi property. But we stand on the shoulders of quite a bit of history here, especially that Fourier family. I mean, think of that academic family. Not only was it Kolmogorov and Shuryev that helped us, but Fourier. I mean, his PhD advisor was Lagrange, whose PhD advisor was Leonhard Euler, whose PhD advisor was Johann Bernoulli, I think, whose PhD advisor was Jacob Bernoulli, whose PhD advisor was Gottfried Wilhelm Leibniz himself, right? So, I mean, I know it's new. I know data science has captivated everyone and is allowing us to solve some really cool problems at scale, both time scale and data scale. But the mathematics of this is anything but new. And in fact, the real gems that let us make progress have been given to us by those who came before us. So that's it. Thank you for your time, and I'll take your questions.